Okay, so we're going to get going. There's still people coming in, but we'll get moving along anyway. So welcome to Fenestration Canada's Tech Talk. My name is Terry Adamson. I'm the technical director with Fenestration Canada. Today's session, translating across the transatlantic to North American and European windows speak the same language. So today I'm joined by Helen Sanders. Helen has over 30 years experience in the glass industry with an MA in natural sciences, a PhD in surface science from the University of Cambridge, England. She's a leader within Technoform, the forerunner leader in polyamide thermal barriers for fenestration and insulating glass edge bond solutions. She's an active leader in the fenestration and architectural community, serving on the boards of the Facade Tectonics Institute, NFRC, IGCC, and FGIA. Helen was named one of US Glass Magazine's top 100 influencers as one of the individuals who are leading their peers in new directions and changing the whole equation of how we look at the industry. So manufacturers in North America are often challenged by clients telling them this company or that company has much better energy performance values than they do. The devil's in the details, and Helen is going to help us understand why they're different, how to address it when faced with it. So Helen, welcome. Let's have at her.
Oh, well, thank you, Terry. I appreciate it. As Terry said, this presentation was really put together as a response to really needing to understand the difference between U factors published for US-based windows and those coming from Europe. And so, we said, do they really speak the same language? And in fact, sometimes I think about, is physics different in Europe compared to in North America? Because we seem to be coming up with different numbers for thermal performance. And realistically, physics really isn't different across the Atlantic. But what we find is that the principles of heat transfer and how they're implemented and the assumptions made are different in North America compared with Europe. And what this leads to is different values for U factor for the same window if calculated in European terms versus North American terms. And it can be up to a 20% difference. It's quite meaningful. And also that leads to us actually finding that there's actually no correlation between the North American U factors that we calculate and the European calculated U factors. So there's no quick rules of thumb. So what I wanted to do here today is kind of explain to you, what are the reasons for the differences, then talk about some of the implications that arise from that. And then at the end, give you some rules of thumb or like questions to ask when faced with U factors for windows so that you can really figure out whether whether you can do comparisons between windows or not. So with that said, let's just take a dive into why the U factors are different in Europe compared with North America. There's four main reasons. One is there's a different approach taken to doing the calculation. Secondly, the calculation methods are different. And then they use different boundary conditions, which I'll talk about in a moment. And then they have different window size assumptions. So let's talk a little bit about the different approaches for the calculation method for U factor. So in North America, we're really just considering the assembly U factor. Most of the U factors we talk about is just the assembly U factor. It's standardized based on particular model sizes. The industry compares performance based on the assembly only. And that's our paradigm in North America. And it can be challenging for for building simulations, for energy simulations, because you really want to use project-specific sizes for that. And really, we only generate model size or U factors based on a model size. In Europe, the situation is different. They calculate U factors for the frame separately from the center of glass, and they also then calculate a performance for the edge as well. What that does is it allows you to calculate an overall assembly U factor as a function of the particular project size and scale it, scale the performance for size.
Helen,
Yes, go ahead.
sorry, I hate to stop you, but I'm being
It's
told
okay.
there's an echo. I
Oh,
don't
I'm
know where
sorry.
it's coming from. I'm not hearing it. So is anybody else getting an echo here that,
No, I'm on
yeah,
my
I'm
end.
not
It's all
hearing it.
good.
It's clear to me.
Um,
Amber,
mm,
it says all of us are echoing. I don't hear it, so I don't know how to fix it.
Sometimes it's the Zoom that decided to use like two speakers instead of only one. So maybe look in the audio button on the left, Amber. It'll probably tell you which speakers are being used.
Yeah. Um, let's see
Do
here.
you want me to
So,
try
okay, Vito
something?
says it stopped.
Okay, so it was more than
Amber,
one.
how about yours? Is it still? Just want to make sure that we're not.
Am I echoing now?
No, you're good.
Okay,
Okay.
I think we're good now. Okay, go ahead. Sorry about that.
That's not a problem. So just to recap, so the Europe really focuses on the individual components of the assembly, and that allows the U factor to be calculated for project specific sizes. And you find that the industry, when they're advertising or talking about windows, is they talk about the component U factors to some extent, at least the same or more than the assembly U factors, which is an interesting difference. So just to dig in a little bit, so the North American U factor is calculated by an area weighting. You calculate a frame U factor, you multiply it by the area of the frame, you then add it to an edge of glass U factor, which is multiplied by the edge of glass area. That edge of glass area is defined as a 2.5-inch strip around the perimeter of the window just inside the sight line. And then you add that to the center of glass U factor multiplied by the center of glass area, which is basically the glass area minus that perimeter edge of glass area. And then once you do that, you get the area of the window is equal to basically the U factor of the assembly multiplied by its area. And then you get your U factor. It's simple. The European calculation is a little different. Instead of an edge of glass U factor, it uses this concept called linear thermal transmittance, or psi value, where it assigns a thermal bridge value, linear thermal transmittance to the conductance just caused by the glass frame interface. And it doesn't assign an area to that, it's just a linear length. So it's basically this linear transmittance multiplied by the interface length of glass to frame. And then that gives you the transmittance caused by the edge of glass. The frame U factor times the frame area, the center of glass, multiplied by the full glass area. Then you add all that together and it gets you the overall transmittance of the window. So it's a little different calculation. And that little difference actually gives rise to some big differences in the outcome. Before we go on to some of the other differences, what I want to just talk about briefly here is that the implication here in both European and North American U factors is that you really have to clarify what the U factor you're looking at is for. A lot of people talk about the center of glass U factor, and they get that mixed up with the whole assembly U factor. but the frame U factor and the edge of glass U factor are typically higher or worse than the center of glass U factor. So when you do the area weighted average to get the assembly U factor, the assembly U factor is typically always higher than the center of glass. So bad things can happen when you mix up that lower or better center of glass U factor with the assembly U factor. And here's just a brief example. So when this is an example of a building simulation just done on the perimeter zone. It's like a little perimeter zone model. It was done based on the Minneapolis climate zone with a 70% window to wall ratio. And what we did was we simulated the perimeter zone, assuming that the center of glass U factor was mixed up and used instead of the whole fenestration U factor. And in this case, the center of glass U factor was about 0.3 in IP units. And that's compared to the whole fenestration assembly U factor of 0.45, so quite a considerable difference. In that simulation, what happened is that if you assume that the mistake was made on all 4 elevations, you actually end up underestimating the perimeter zone heating energy use by 28%. And the typical perimeter zone energy use intensity by 15%. So that's huge. I mean, you could really end up having some big design oopses, especially with perimeter zone HVAC sizing. So it's really important to make sure that you differentiate the central glass U factor from the whole fenestration U factor, because they are definitely not the same and they are typically quite different. So that's one reason why the European and the US and Canadian U factors are different, because we have a different approach. But also the calculation methods are different, and it all stems from the parent or the mother ISO standard, which is ISO 15099. And it is a standard that tells you how to calculate the thermal performance of windows. And it gives you 2 approaches. It gives you basically the North American approach, which is the area weighted method, or it allows you to do the linear transmittance method, which is basically the European method. So you have 2 parallel methods. North America chooses the first and Europe chooses the second. And as a result, and this is where a lot of the differences come from. So the linear transmittance method, the European standard references that, and it also and that's in the EN 10077-1 standard, and it also references a different calculation method for calculating the center of glass U factor and also the frame U factor. But basically, what the biggest differences are that the area weighted method, when you look at the frame U factor, it includes some of the heat transfer due to the spacer and the edge of glass, whereas in the linear transmittance method, the U factor of the frame doesn't. So even at the component level, you cannot compare a U factor calculated from the European method with a U factor calculated through the North American method. What we find also is that NFRC 100 has a much more rigorous center of glass U factor calculation, and it also calculates skylights at an incline, whereas in contrast, the European method has a more simplified calculation method for central glass U factor and uses the slope glazing at a 90-degree slope for comparison. It also has some different default material conductivities that you can see influencing the end result as well. So calculation methods are different, approach is different, and one of the biggest influences are the boundary conditions. And what I mean by boundary conditions are the temperature assumptions and wind speed assumptions and all the assumptions relative to the climate. In North America, we have an outside assumed temperature of -18, whereas in Europe, it's 0, just freezing. So a lot more, a milder assumption for climate. The interior temperatures are pretty similar, one's at 21 and the other's at 20, but the delta T, the difference between inside and outside, is much, much higher for NFRC 100 versus the European standard. And that gives rise to some significant differences, just purely when we think about the boundary conditions themselves. Even if you use the same, even if you use the NFRC calculation methodology and you change the air temperatures, you're going to see a big difference in U factor. The other thing that's different in the boundary conditions are what we call these surface film coefficients. Just think of those as reflecting the conductance or resistance of the boundary layer that occurs between a solid surface and the adjacent air, and the heat transfer that occurs across that boundary. And it occurs through convection and radiation, and it's influenced by the wind speed, it's influenced by the orientation of the surface, the slope of it, it's influenced by the temperature difference and the emissivity of the surface. And really, just in simple terms, what we find is that the assumptions that NFRC uses are significantly different to the assumptions that ISO uses. What we find is that there's a range. NFRC uses a range depending on the frame material, on the slope, but ISO has less variation. The other thing to note is, as the fenestration performance gets better, the differences caused or influenced by these, the differences in surface film coefficients increases. So you see differences becoming more apparent when you get better fenestration performance. So boundary conditions are huge. The other difference is window size assumptions. So in NFRC, as you know, there's a huge list of different sizes for different windows. For the European standard, there's no standard size. And you typically calculate the U factor for the particular window size in question. Now, a passive house, which uses the European standard, does actually set one window size for comparison, but that window size is still not comparable with the NFRC sizes. So lots of difference. I would refer you to a really, really very good review by RDH that they did for BC Housing. I put a link here in the presentation if you want to dig down deeper. But basically, there's lots of differences, and as Terry said, the devil's in the details. But the main takeaway is that you really can't compare European and North American U factors because they're just not the same. And the impacts are quite significant. So I want to just take us to one of the key parts of window design, which is the optimum cavity dimension for an insulating glass unit. So heat transfer, or U factor, depends on the conduction across the cavity and the convection in the cavity. As you increase the cavity dimension, conduction goes down, which is great. You would think that U factor would go down. But as you continue to increase that cavity dimension, you start to build up convection currents. So then the heat transfer starts to increase. So what happens is you end up with an optimum cavity dimension that optimizes the combination of conduction and convection. So there's this optimum or minimum U factor that occurs. And you will see this, you know this, because in North America, we typically design all our windows around 12 to 13 millimeters, half an inch, because that's the optimum cavity dimension for air and argon. Now, the optimum cavity dimension, as you see in this graph here, depends on the gas, and it depends on the gas conductivity. The better or the lower the gas conductivity, the smaller the cavity you can have to get to the optimum. So the optimum cryptum cavity is about 7 to 8, 9 millimeters. The optimum argon is about 12, and the optimum cavity for air is about 13. Again, that's why typically our windows are designed around a ½ inch plus or minus cavity. So I want to show you here in this next slide, and this is center of glass U factor. I want to show you the center of glass U factor as a function of cavity dimension for a center of glass that's calculated using the NFRC method and the NFRC boundary conditions, compared with the center of glass U factor calculated using the NFRC method, but using the ISO EN boundary conditions. And you can see why when you look at European windows are designed around a 16 millimeter cavity dimension, because that ends up being the optimum when you use their boundary conditions. So the boundary conditions end up defining what the optimum cavity dimension is. And so you can see the difference that makes. 12 to 13 millimeters versus 15 to 16 millimeters for the different European, North American boundary conditions. So it really influences the window designs. So what we find is that the two different calculation methods give for the same window. If you picked one window at one particular size and you did those the European method and you use the North American method, you would get two completely different U factors. And they can be up to 20% difference. And the center of glass could be even more different than the assembly value. And that's even if you use the same window size. So what that really means is you cannot, especially in Canada where you use metric units, metric U factor units, it's really important that you don't do a direct comparison between a European metric U factor and a North American metric U factor. They are not the same. And you can't change a European calculated U factor in watts per meter square Kelvin metric and turn it into an IP unit U factor and do a comparison with NFRC 100. It is just not possible. Don't do it. There's also no rule of thumb that we can give you that correlates an NFRC U factor with the European U factor. European U factors can often be lower, but they can also be higher than the NFRC value as well. So there's no quick rule of thumb I can give you other than just don't compare them. It's not possible. So I've just put on the screen here 5 questions that it's really important to ask about a U factor. If you're given a U factor from a customer, from a supplier, from anybody, ask these questions. So first of all, what is the U factor describing? Is it for the whole window assembly? Is it just for the center of glass? Is it for the frame? You really need to know what it's describing for you to understand the context and how to use it. The other question, probably obvious, is what's the units? Are they watts per meter square Kelvin? Are they in IP units? And then what's the calculation standard that was used to generate it? Was it NFRC 100 or was it the EN ISO standard 10077? And what were the boundary conditions used? Were they NFRC winter boundary conditions? Or were they European boundary conditions? Because that, as you saw before, makes a big difference to the U factor outcome. And then also, what was the size of the fenestration that was used in the calculation? Because that obviously has a big impact, because that determines the frame to glass ratio, which has a big impact on the overall assembly U factor. So you need to know, was it project specific? Was it the NFRC model size, or was it something else? And then you might want to ask, if you're dealing with skylights, was it a U factor for a skylight? And you really need to confirm the orientation of the simulation, because whether you do it at 20 degrees or whether you do it at 90 degrees or anything in between, again, makes a big difference to the outcome. So these are my rule of thumb questions. And then just before we finish up here, there's some other important takeaways from the edge of the glass. So if you saw the calculation for the assembly U factor, it's pretty clear that the center of glass U factor is not in any way impacted by the edge of glass performance, because it's the definition takes it away from the edge of glass. The spacer and the edge seal thermal performance in Europe impacts the psi value, that linear transmittance at the interface with the frame, and of course the U factor of the window, the assembly. In North America, the spacer and the edge seal impacts obviously the edge of glass U factor, but it also affects the frame U factor and of course the assembly U factor. So this is something to be aware of when you're looking at across the Atlantic. So the edge of glass U factor in North America depends on the spacer and the sealant, of course. It also depends on the IG makeup and the gas content and the frame bite. The psi value, that linear transmittance, really depends on the frame interaction with the edge of glass. So it depends on the bite and the frame material, which in North America, the edge of glass does not depend on. And of course, it depends on the spacer and sealant and IG makeup, just like in Europe, so in North America. So be very clear that the psi value and the edge of glass U factor in North America are not equivalent, and you can't mix them up. And with that note, I'm going to finish up and answer the questions. The question, does the EU and North American windows speak a different language? And the answer is yes, they do. And translation is super hard. So proceed with caution. Don't do it.
Great. Thanks, Helen. So a couple of quick points. Whenever Helen said NFRC, you can insert CSA A440.2. They're essentially the same. So lots of Canadian manufacturers use the CSA program. And many, many times in my career, I was, I had a salesman come to me and say, well, their casement window gets a 105 metric and we're at 1.5. How come? Well, center of glass values. So if the performance is way out of whack and the product is comparable, oftentimes that's your answer, is they're being given a center of glass. So I asked Adrian Edge to join us today. Adrian's our codes and regulatory director. Adrian's been doing a lot of work connecting to European entities. For instance, IFT Rosenheim is a standards organization in Europe, working on a lot of this kind of topic and questions and imported products and what it means when imported products come in with European standards. So first thing I'm going to do is give Adrian a couple of minutes here to kind of elaborate and ask any questions he has. and then we'll open it up to anybody else that has questions.
Awesome. Thanks, Terry. And Helen, great presentation. Thank you very much for taking the time and unpacking. It's really it's a tough subject. And frankly, I think as we move forward, it's going to become more important. I was just doing a little bit of looking over the last couple of days, and there's, maybe 5 or 6 research studies out there right now that have started to do some of this comparison work. To Terry's point, I'm really grateful. Roland from IFT Rosenheim actually came in and got to watch the presentation today, and my conversations with him have been great. We're admittedly really early in some of those discussions, but I'm looking forward to spending a bit more time to understand. I really struggle with your comment on there's no correlation possible. Like everything in my being wants to believe, what's the standard deviation here? Like, what do you mean it can't be correlated? Is there some way for us? But I can see the methodology just is so abstractly different. It's like the truth is if we're looking for a level of accuracy, if accuracy matters, and I think as we move forward to more like net zero, more thermally efficient home type of solutions, that accuracy is really important to get down right. Yeah, there just may not be a variation possibility within these two opportunities that quite work together. And I know working on passive house homes in the past and some of the seeing specifications where they called out EN ratings before we even started the conversation was really challenging. So I guess my question is, there's obviously going to be I'm going to poke at North America. That's what I'm going to do with this. Is what of these two methodologies would you consider more accurate?
I don't know if there's an accuracy. I mean, I think if you look at the base calculation methodology, it would point to North America just because it doesn't use the estimates and approximations that some of the like the EN 673. And I guess I would also say, like, I am not an expert in all the details. I don't use those calculation methodologies. So this is just an opinion based on what I read. The folks at LB&L have done some great work in this area. Folks at RDH have done some great work on reviewing too. So I think that's a hard one. I think maybe precision is also an interesting question, because when we're talking about and I don't know whether accuracy, I guess accuracy is important. We get a good correlation. I think NFRC, CSA get a good correlation with the physical measurements, and they have to be within 0.02. The challenge that I think we have as in the manufacturing field is that level of accuracy, plus or minus or within 0.02, is big relative to the numbers that we are playing with in order to meet code, right? If the code says you need to be at a 3.0, it doesn't really matter if you're a 3.2. You got to be at a 3.0, and typically that means you have to be at a you can't be higher than a 3.0499, right? So
I'd love to chime in there, because accuracy, precision, variability, those have been really big conversations the last few years. Helen, I don't know if you followed any of the work that Fenestration Canada did with the City of Vancouver and their energy modeling guidelines, where they require size specific, project specific values.
Yes, that's great.
We created a calculator that will take NFRC and CSA data and do that work. So when we talk about is one better than the other, is the European methodology more precise in using site size specific values?
Yeah, I mean, I think that I think that part of the approach is important. And I really applaud what you've been doing in Vancouver. And we've been trying, we as in the Facade Tectonics Institute, and Techniform, and actually some of our industry associations too have been trying to change the model codes in the US to allow size-specific U factors. And NFRC 100, the commercial approach, now allows, it gives you a calculation methodology to do size-specific. But I think it depends on, are you using size-specific for modeling? Are you using size-specific for code compliance? Or are you using size-specific for comparison? So clearly size-specific for comparison for sure makes sense. Size-specific for modeling doesn't. And I'll tell you, the people I collaborate with at the Facade Tectonics Institute, those practitioners will tell you that design teams will play the game. Where it helps them, they'll use size-specific for modeling. Where it doesn't, they'll use the standard size. So we need to be very clear. The codes need to be way clearer in that regard. So yeah, I think size-specific for modeling, size-specific for code compliance, for the performance path makes sense. For the prescriptive path, maybe not. But I think where there is a significant argument to be made is in the temperature boundary conditions. But you don't have to throw the baby out with the bathwater to change the boundary conditions. You can still use the NFRC approach and have a different conversation around what might be appropriate boundary conditions. Now in Canada, I'm pretty sure that -18, I don't know if it's normal, but you certainly get -18. Perhaps not in Vancouver.
Not where I am, no.
Yeah.
No, I do definitely get that on a normal day up in my neck of the woods. But it's a great conversation that you're kind of pointing to, and we've been having this a lot, both at our conferences and behind the scenes, is the difficulty we're running into is we're looking at, call it the apples to apples model that we have developed, which I think worked really well for, call it a building code type of environment. When we're just trying to set prescriptive requirements, apples to apples is excellent. Like it does something that actually many, I think, international codes, as I'm looking at them, have really struggled with. But alternatively, we've left ourselves with kind of this gap where once we get to the actual project side, and we actually need accuracy to the degree that we're talking about as we're getting close to net zero homes, that's a problem. Like our apples to apples comparison no longer is viable. We just can't have that level of you call it modeling inaccuracies built into the model itself. So I made some comment earlier today, and I've been kind of chewing on it. It's like, man, what we really need is our model code to run the gamut of health and safety. Like we need the ability to set some basic standards on what's expected. We also kind of need the second path, which a lot of times Passive House and the CHBA Net Zero stuff and LEED and all of these other programs are acting as like market directions for best practices. You almost need like two pathways in order to deal with this particular conversation, because dealing with it within the model code itself is kind of dangerous, frankly. Like you get into this place where the model code takes on responsibilities that may be wholly inappropriate for meeting basic requirements. But as we progress in our expectations of our buildings, we actually do need this separate path. We need the ability to build in accuracy and understand how the buildings work without having to compromise, one for the other. So it's a really important conversation.
Yeah, and it goes to what are we using the U factors for? And I agree with you. I think the boundary conditions we should look at, and certainly size specific. And that's something that I've been advocating for a couple of code cycles now, is to have size specific U factors in the performance path. But there's the other thing that I think that is an opportunity is what Passive House I think does a nice job of is looking at the performance of the interface with the wall.
Yeah.
So, and that's something which we as an industry haven't really got our arms around, but there's potentially an opportunity there to look at that interface.
So Patrick's got a couple points, but I just want to ask something about, if you're aware of any work being done. So when we did the size specific work with the City of Vancouver, one of the questions that came up multiple times was, what about structural components within assemblies that don't get captured in NFRC or CSA? Oftentimes, composite window designs, multi-light products with mullions that are full of reinforcing, that thermal bridge doesn't get captured anywhere. We're actually going to start a project soon to look at that, but I'm wondering if you've done any of that work, or if you know of any of that work that's gone on.
No, but I think that's identified by the leading practitioners, is that the thermal bridging issues are becoming bigger than the clear field transmission. And we are missing that, and air leakage are driving the thermal issues on buildings, because we are doing a pretty good job with the windows themselves. It's the air leakage around, not through the windows themselves, but the other interfaces on the building, and the thermal bridging. And the thermal bridging in spandrel, that's another area that we aren't, I think there's work, obviously the Pankow Foundation are sponsoring some work on that right now.
Yeah. Well, hopefully we'll get some answers in the work we're going to do. Okay, Patrick's got a few comments here, Patrick Flannery. So if you made a window to export to the EU, I don't know if you're going to have an answer here, but is there anybody in Canada that are testing to the EU method? I actually think UL might be. I know that there are accredited labs in China, for example, that is doing North American NAFS testing. So why wouldn't we have labs that are doing European testing for products being exported? I don't know for sure, Patrick. I don't know if anybody in the call is aware. I kind of recall something from UL though that was doing that.
I don't know. I mean, I don't really know what the balance of trade is, but my guess is it's certainly more coming into North America than going out of North America.
Yeah, that would be my thoughts, is that the demand for, call it, North American products tested to EU standards, probably not very high. Like trying to get products out that way would be challenging.
Well, and there's, we think we have additional test standards here, but there's certainly additional testing that you have to go through to sell into France and to sell into Germany. So, there's some other barriers that one has to get over.
Yeah, okay. I love this question, Patrick. How do you explain all of this in 30 seconds to a client who's being blown away by European claims? The elevator pitch. What's that 30-second?
I think you say the calculation methods are very different. They are just not comparable. I mean, I think they're just so different. You cannot compare a U factor from North America and Europe.
You said this right at the beginning, Helen, and I love this. Like, it's one of the catchy things that I think is helpful in that. Thou shall not compare.
Yeah, there you go.
Just physics is different between
and another comment from Pat. I don't know if there's an answer for this, but how much variation do the differences in calculating edge transmission create? Again, you already said that, there is no, here's the 20% better, 10% better. Is there, a difference in that edge transmission that is calculable?
Sorry, I'm
so
trying to understand.
The question is, how much variation do the differences in calculating edge transmission create?
I'm not sure that that's huge. I think the biggest differences in because it kind of washes out in the overall assembly calculation. The biggest issue comes from the boundary conditions and the actual assumptions that are used. I think the biggest challenge with how Europe approaches the U factor calculation is the fact that because they're considering all the three components separately, and people tend to say my frame is better than yours because my U frame U factor is X, and they also do the same for the edge of glass, so the psi values, and so because the edge of glass is the smallest contributor by area, you end up, because when you think of that individually, a 10% improvement or a 20% improvement in the edge sounds great on paper as an individual component, but when you put it into the window, it washes out. And one of the things I'm very concerned about is that you don't end up, when you try and reduce the thermal conductivity of the edge too much, you end up taking material out, dematerializing it. And you have to have a appropriate balance between the thermal performance and the durability. And so I think that's one of the unintended consequences of a focus on the individual components without looking at the influence on the whole assembly.
Okay. A request for the presentation, just a side note to that is all of our content is recorded. So you'll be able to watch this again and again and again and again on our website, FenCan Videos, or our YouTube channel, Fenestration Canada YouTube channel. Now, Helen, I don't know if you want to share this with anybody, if somebody was to reach out, if
absolutely.
You would, right? So
just email me. My email is at the end of the presentation, but it's helen.sanders@technoform.com.
Perfect. Okay. Any other questions from anybody? Going once, going twice. Helen, I want to thank you so much. Finally able to connect with you and do something. It's been on my list to do for a long time. And when I read this article, I thought, there's the opportunity. We need to get together and chat. So
well, it's
really
a pleasure. And I would say that you guys in Canada are really leading the way, especially in Vancouver. So
yeah, much
I'm going to pick your brains
strength
about how to get it done at IECC on the code side.
Yeah. Vancouver is very aggressive in their stance around efficiency and enforcement as well. We've been working with them on that lane quite a bit lately. So it's interesting that the most aggressive jurisdiction is probably the warmest one in Canada, but that's a story for another day. So Helen, again, thank you so much. I really appreciate it.
Thank you.
Thanks everybody for joining us. Adrian, thanks for your input. And we'll see you all at our next Tech Talk. Thanks a lot.
Thank you.
Bye-bye.